Associate Professor, Department of Chemistry, A.D.M. College, Nagapattinam. Today we see covalent bond. This unit belongs to first BSc Chemistry in General Chemistry 1 for Unit 3. This is the Module 2. In the previous module, we see chemical bonding. What is meant by chemical bonding? What are the types of bonding and formation and conditions, measurement of ionic bond. In this module, we see covalent bond. Covalent bond. What is meant by covalent bond? A chemical bond between two atoms in which a pair of electrons is shared by both participating atoms is called a covalent bond. Each of the two containing atoms contributes one electron to the electron pair and has equal claim on a shared pair of electrons. This concept of covalent bond, we need theories which would answer the questions like why covalent bonds are formed, how the electrons are arranged in a space in molecule, how the sharing of electrons could explain the geometry of the molecule. Development of the wave mechanics has led to the two theories. One is valence bond theory and another one is molecular orbital theory, that is VBT and MOT. Now, let us see the valence bond theory for the formation of hydrogen molecule. In the valence bond theory, describes the covalent bond and the covalent bonding in molecules in a quantitative manner. It is based on the overlapping of the two atomic orbitals in the formation of a bond. According to this theory, each atom uses electron in one or more of its valence orbitals to form covalent bond. Now we see the example. In a hydrogen molecule means that is H2. That is composed of two protons, Ha and Hb, and the two electrons, E1 and E2. Let us consider the first instance, two hydrogen atoms lying far apart from one another, so that no interaction between them is possible. Let the wave function orbital for the electrons in a separated atom is represented as psi A1 and psi B2. Then the total wave function will be given as psi, that is equal to psi A1 and psi B2. Using the wave function psi, it is possible to calculate the energy of the system. When two atoms are removed far away from one another, that is the internuclear distance is infinity, the total energy of the system is zero. As the atoms are brought closer in the region is which the electric field due to one can influence that the other, the energy of the system starts decreasing till the minimum value is reached. In the curve A shows in the figure, the stage 2 corresponds to the formation of hydrogen molecule. A molecule of hydrogen, the internuclear distance at this stage is should to be R0. That is A, that is psi is equal to psi A1, psi B2. And B, that is in a psi symmetrical, that is psi A1, psi B2 plus psi A2, psi B1. And in the C graph shows that psi antisymmetrical, that is psi A1, psi B2 minus psi A2, psi B1. There is no defect in the calculation. The bonding energy is only 6 kilocalories per mole. The experimental value is 104 kilocalories per mole. Why this difference? We should assume that the electrons of the two hydrogen atoms could be distinguished from each other, therefore labeled as 1 and 2. This assumption cannot be correct because no longer the electrons 1 will always be nearer to the nucleus A and the electron 2 will always be nearer to the nucleus B. The system of the hydrogen atom may then be represented by two different states, first state and second state. HA, that is the electron 1, HB, electron 2 in the first state. In the state 2, HA, electron 2, HB, electron 1. Instant in a first state, the nucleus A is associated with the electron 1 and the nucleus B is associated with the electron 2. But in state 2, on the other hand, the nucleus is associated with electron 2 and the nucleus B is associated with electron 1. If psi 1 and 2 are the wave functions and the states 1 and 2 respectively, that we can write as psi 1 is equal to psi A1, psi B2 and the psi 2 is equal to psi A2, psi B1. Now the law of linear combination can be used for calculating the wave function psi. It is two possible wave functions. One is symmetrical combination and another one is the anti-symmetrical combination. In the symmetrical combination represented as psi s, that is psi s is equal to psi a1, psi b2 plus psi a2, psi b1. In the anti-symmetrical combination represented as psi a, that is psi a is equal to psi a1, psi b2 minus psi a2 minus psi b1. The anti-symmetrical wave function leads to increase the energy. Thus, the bonding is not possible in the anti-symmetric state. That shows in the curve C. In a symmetrical wave function leads to fall in the energy, and that is shows in the curve B. That bonding is possible in this state. The next theory for the important one for the covalent bond is VSEPR theory. That is valency shell electron pair repulsion theory. In this theory states that for maximum stability of a molecule, the orbitals occupied by electrons in the valency shell of the central atom should be so arranged in space that they lie as far from the one another as possible. This theory also given in the forms of the postulates. There are the 3 points. In the first point, the formation of simple covalent molecules, there is one central atom which forms in the covalent bond with other atoms. In the formation, second one, in the formation of covalent bond, orbitals get occupied by electron pair when the central atom forms more than one covalent bond. There will be more than one such orbital surrounding the central atom. Since the electrons experience in the electrostatic repulsion from one another, the orbitals containing electrons also experience in the similar electrostatic repulsion. The orbitals therefore tend to keep apart from one another as far as possible. That is, in the first postulate. Now let us see the first postulate. In the formation of a molecule of water, the central atom of oxygen which forms two covalent bond with two hydrogen atoms. Similarly, in ammonia, nitrogen NH3, nitrogen is the central atom. In the methane, CH4, carbon is the central atom. So, it will surrounded by one or more covalent bonds. In the second postulate, that each bond surrounding the central atom will have a pair of electrons. That is mainly for the covalent bond. In the third one, the electron pair in the covalent bond repel to each other. Because of this repulsion, the bonds tends to keep away from one another so that they experience minimum repulsion. This provides them definite shape. This VSEPR theory applies not only the orbital containing shared pair of electrons, but also to the orbitals containing lone pair of electrons. This arrangement of orbitals in space minimizes the force of repulsion between them. The molecule therefore has minimum energy and maximum stability. Using this theory, we have to determine the shapes of a simple inorganic molecule. First one is the linear shape. In the linear shape, we have to see beryllium chloride BeCl2, HgCl2, BeF2. If there are only two orbitals present around the central atom in a molecule, the only way to keep from far apart is to arrange them linearly. The angle between that is ClBeCl is 180 degree. These are the other two examples for HgCl2 and BeF2. Be is the central atom for the beryllium fluoride, and mercury chloride HgCl2 mercury is the central atom. In the second shape is the bend structure. Bend structure example is water molecule. In a water molecule, the oxygen atom is the central atom. Has the two bonding electron pairs and two lone pair of electrons in the water molecule. Oxygen containing two bonding orbital and two lone pair of electrons. The electrostatic repulsion between them lead to the tetrahedral arrangement. The bond of the oxygen atom will be directed to the two corners of the tetrahedral and the lone pair towards to the other two. Since the non-bonding electrons repel more strongly than the bonding electrons, the two bonds will be forced closure. Thus, the normal tetrahedral angle 109 degree 28 minutes is reduced to 104.5 degree. The water molecule assumes the V-shaped bend structure. Next one is the pyramidal shape. In the pyramidal shape, we see the example is the ammonia molecule. Ammonia molecule formula is NH3. In the central metal atom is the nitrogen. Nitrogen containing 3 bonding pairs and 1 lone pair of electrons. Because electrostatic repulsion, it is expected that the 3 covalent bonds will be directed to the 3 corners of the tetrahedron, while the lone pairs will be directed towards the 4th corner. According to VSEPR theory, the lone pair of electron exceeds the greater repulsion in the bonding pair. As a result of the 3 bonding of ammonia molecule are forced slightly closer together, leading to pyramidal structure with the lone pair of the top of the shore. Other one example for the pyramidal shape is the BF3. The fourth one is the octahedral shape. We see the example for SF6. In the SF6, that is the sulfur is the central metal atom. If there are 6 orbitals around the central metal atom of a molecule, the molecule has a shape of regular tetrahedron. The bond angle is 90 degree. Sulfur hexafluoride is an example for this type. The structure is shown in the figure. And the fifth one is the trigonal bipyramidal. Example of the molecule is PCl5, phosphorus pentachloride. If there are given orbitals around the central metal atom in the molecule, the only way to keep them far apart is to arrange in the trigonal bipyramidal structure. That is shown in the figure. That is in an angle for phosphorus, chlorine. Chlorine is the 2 angles are that 120 degree and also 90 degree. In a linear structure, that is ClPCl is 90 degree and the ClPC for the 120 degree. That is in a trigonal bipyramidal. The next one is pentagonal bipyramidal IF7. If there is the 7 orbitals around the central atom of a molecule, the molecule shape as the pentagonal bipyramidal. Example is iodine heptafluoride, and the xenon hexafluoride is also example for the pentagonal bipyramidal. In this shape, that is iodine heptafluoride, iodine molecule is the central atom and the 7 fluorine atoms are arranged in a pentagonal bipyramidal. In xenon hexafluoride, xenon atom bonding with the 6 fluorine atom and 1 lone pair of electrons. So, in the both have the iodine heptafluoride and also xenon hexafluoride is also the example for pentagonal bipyramidal. In the 7th one, that is for the last, the tetrahedral shape. We have already known familiarly to know the tetrahedral shape. The example is the methane molecule. In the methane molecule, carbon is the central metal atom. If there are 4 orbitals around the central atom in a molecule, the only way to keep them far apart is to arrange them tetrahedrally. The bond angle is 109 degree 28 minutes. The molecule gets tetrahedral shape. This is an example for methane and also xenon SiF4. Another example for tetrahedral is Si. Next we move to the molecular orbital theory. Before molecular orbital theory, we know some basic concepts. What is meant by orbital overlapping? What are the types of orbital overlapping? What is meant by hybridization? And what are the types of hybridization? In organic compounds containing covalent bond, a covalent bond is formed by the sharing of pair of electrons between 2 atoms. This is already known. For this purpose, the 2 atoms must be so located that an orbit, one of the combining atoms, overlapping with the orbital to the another atom. Each combining orbital containing 1 electron. The strength of the chemical bond is proportional to the extent overlapping of the orbital. What are the types of orbital overlapping? SS overlapping, SP overlapping, PP overlapping. Now let us see one by one. SS overlapping, that is S orbital overlapping. So one of the S orbital of the one atom overlap with the one of another S orbital of the another atom to form a covalent bond. It is the example that is for SS overlapping. Example for hydrogen molecule. In one hydrogen atom S orbital, because hydrogen atom contains 1 electron, in the hydrogen molecule means that the 2 hydrogen atom containing 2 electrons, that the 2 orbitals are overlapping, SS overlapping to form as a sigma bond hydrogen molecule. And the second one is the sp overlapping. The s orbital of the one atom overlaps with the one p orbital of the another atom to form a covalent bond. It is called sp overlapping. In hydrogen atom, s orbital overlap with the p orbital of the fluorine atom is overlap to form as a sigma bond, that is sp overlapping. And the next one is the pp overlapping, that is the p orbital, one atom of the p orbital overlap with the one p orbital of the another atom to form a covalent bond. That is the molecule of the fluorine molecule. In the fluorine molecule, the fluorine atoms, 2 fluorine atoms must overlap to form as a pp overlapping to form as a sigma bond. What is meant by sigma bond and pi bond? The sigma bond means when the 2 bonding orbitals overlap to form a molecular orbital, which is symmetrically distributed about the nuclear axis, joining the nuclei. When the bond is so formed is called the sigma bond. Sigma bond was formed as a result of the orbital overlapping, s orbital of the one atom and the s orbital of the another atom. Second one, s orbital of the one atom and the p orbital of the another atom. Third one, p orbital of the one atom and the p orbital of the another atom. That is the formation of hydrogen molecule, hydrogen fluoride and the fluorine molecule. Pi bond. When a 2 pi orbitals overlap in this side-wise fashion or laterally to form a molecular orbital, then the bond so formed is called a pi bond. For a laterally overlap, the 2 orbitals must be held parallel. That is, the molecular orbitals thus formed lies above and below the nuclear axis. That the example is oxygen molecule. In an oxygen molecule, that the 2 oxygen atoms must share the electron. In the head-on overlap to form as a sigma bond and the side-wise overlap it forms as a pi bond. Thus, the oxygen molecule there are the 2 bonds is formed. One is sigma bond and one is pi bond. Both are there together is called a double bond. So we can written oxygen, double bond, oxygen. In the another one example for the nitrogen molecule. In a nitrogen molecule, there are the 3 bonds. One sigma bond and 2 pi bond. All the 3 bonds put together are called as a triple bond. That in practice to written like this, N triple bond N. So what is the difference between pi and sigma bond? The sigma bond has an increased electron density in the internuclear region than in sigma bond. But in sigma bond, the electron density is concentrated along the bond axis. If the pi bond, it is concentrated above and below the bond axis. Pi bond is weaker than sigma bond. Because the extent of overlapping, the internal energy than that of the sigma bond. And hence the decrease in the internal energy of the system is less. Third one, there is no free rotation of atoms about the nuclear axis in a pi bond. Because during rotation, the coplanarity of the overlapping of p orbital would disappear. So, the extent of pp overlapping decreases, the energy of the system would increase. Thus, the rotation about the bond axis of a pi bond would be restricted because work will have to be done for the same. Because of this restricted rotation, many pi bonded compound exhibit cis and trans isomerization. And what is meant by hybridization? What are the types of hybridization? How will you explain the hybridization in a molecule? Let us see. In the shapes of the orbital and the formation on various types of bond, but these concepts are not enough to explain the observed shapes of the various molecules. So, to account the shapes of the various molecules, the concept of hybridization was introduced. Now, let us see that the CH4 methane molecule. It is assumed at the time of the bond formation, the carbon atom attain an excited state. In the excited state, 2s electrons are unpaired and one of them are the promoter to 2b orbital. In the ground state electronic level, carbon has the 1s2, 2s2, 2p2. But in excited state, electronic configuration is 1s2, 2s1, 2p1, 2px1, 2py1, 2pz1. Now, the tetravalency of the carbon has been accounted for by proposing the excited state structure for carbon atom with 4 unpaired electrons. The 4 unpaired electrons are not identical. There is 1 s electron and 3 p electron. They explain the equivalent nature of the 4 bond of carbon in its saturated compound, new concept called hybridization. According to this concept, the atomic orbital of an atom which lie close to one another in energy tend to merge or mix and then redistributed their energy and shape to produce an equivalent numbers of new orbitals which are identical to all respects called hybridization orbital. That is the hybridization orbital. Hybridization is defined as is the concept of mixing or merging of orbitals of an atom having nearly equal energy to produce entirely new orbitals which are equal in number to the mixing orbital. The hybridized new orbitals will have equal energy, identical shape and are symmetrically placed in condition. What are the conditions for hybridization? The orbitals of an isolated single atom only could undergo hybridization. The hybridizing orbitals must differ only slightly in energy concept. So, what are the characteristics? The number of hybridized orbitals is equal to the number of pure atomic orbitals which mix up. The second one, an hybrid orbital can have only 2 electrons are a pure atomic orbital. The 2 electrons must have opposite spin. The electron waves in the hybrid orbitals repel each other, so then tend to be as far as away possible. Fourth characteristics of hybrid orbitals are, it is distributed themselves such a way that they assume the direction on the domaining orbital. Then what are the modes of hybridization? That is sp hybridization. One s orbital and one p orbital mix and give 2 identical hybrid orbitals. This is known as sp hybridization. The example for BeCl2, because the beryllium in the s orbital and the chlorine in p orbital to form 2 sp orbitals, that the bond angle is 180 degree. In the sp2 hybridization orbital, the simple example is ethylene. One s orbital and the 2 p orbitals mix and give 3 identical hybrid orbitals. This is known as the sp2 hybridization. In the sp2 hybridization, bond angle is 120 degree. In the sp3 example for the sp3 hybridization is the methane. One s orbital from the carbon atom and the 3 p orbitals from the hydrogen atom to form 4 sp3 hybridized orbitals. Because in the excited state, electrons in a carbon atom excited state, 4 electrons are the unpaired electrons, so that it gives the 4 sp3 hybrid orbitals. The bond angle is 109 degree 28 minutes. This module we have seen the covalent bond, theories of the covalent bond in the VBT, and what are the basic fundamentals for in the MOT. Before we go into MOT theory, that what is mean by orbital and what is mean by hybridization orbital, that we know in this module. In the next module, we have see the molecular orbital theory for the covalent bond. Thank you.